Thanks, Chair, for the introduction. And my name is Rong Yu from Renmin University. And I will first thank the organizers for inviting me into this wonderful online workshop. And today I would like to share with you with our recent results on the electron correlations and optical selectivities in this double-layer nickelate superconductors under pressure tuning. And I will first thank my collaborators. Mr. Zhiguang Liao and Guijing Duan are my graduate students at Renmin University of China. And we also collaborated with Dr. Chang'e Liu at Dali University and with Professor Chimia's group at Rice University, and also with his graduate student, Mr. Lei Chen and Yiming Wang. So here's an outline of my talk, and I will first give a very brief introduction to this orbital selectivity, which can be viewed as a multi-orbital correlation effect in the general multi-orbital correlated system. And then I will discuss mainly the correlation effects and orbital selectivity in this bilayer nickelate superconductors. And then I will move on to discuss the effective TJ model and the superconductivity in this compound, and finally summarize my results. Okay, so as Professor Wang just introduced, recently the high TC superconductivity at around 80 Kelvin has already been observed experimentally in this bilayer nickelate compound under pressure tuning. And very recently, the zero resistance has been also confirmed by these two groups. And also this diamagnetic response has been measured. And I also think that in tomorrow's talk by Professor Li Lingsun, she will discuss more detail on this. And then immediately after the discovery of high TC superconductivity in this compound, there emerges numerous theoretical works. And here I just give a very incomplete list, which by posted on archive by the end of July last year. And there are more than 30 theoretical works. And ours is actually among them. And we are actually particularly motivated by two experimental findings. Those are the spectral measurements. One is the optical conductivity measurement by Professor Haihu Wen's group, and the other is a RPAS measurement by Professor Xinjuan Zhou's group. So in the optical conductivity measurement, I find a substantially suppressed Joule weight, and also the corresponding experimental kinetic energy of the electrons is found to be reduced by a factor of 10 compared to the band theory value. And in the RPAS measurement, they find that the system contains multiple sheets of Fermi pockets, so with different orbital characters, so that this is indeed a multi-orbital system. And also, they measure the mass enhancement factor along different cuts in the Brillouin zone, and find that the mass enhancement factor indeed shows a very strong orbital dependence. So this actually reminds us that there could be very strong orbital selective electron correlations in this bilayer nickelate system. And then this effect, this orbital selective mode behavior, has already been extensively studied in the iron-based superconductors. So remind us that there could be some similarity between these two systems. So in general, for a multi-orbital system, with, say, this transition method with 3D electrons. And we actually are particularly interested in all these orbitals contribute equally to the superconductivity. But in most of the cases, the answer is not. So there are indeed some systems with a particular strong, correlation effects. And the extreme case in the normal state is called a orbital selective mode phase. And here I show just a cartoon with a two orbital system. And in this orbital selective mode phase, it actually corresponds to that in one orbital, the electrons are all mode localized. And in the other orbital, the electrons are still itinerant, which behave a metallic behavior. And in experiment, this can be measured through the mass enhancement factor, which should show this very different factors with different bands when they are dominated by different orbital characters. So this can be this orbital-dependent mass enhancement factor can be seen as a precursor to this orbital selective mode phase. And to understand the orbital selectivity and orbital selective mode behavior, theoretically, we actually consider a multi-orbital Hubbard model. And this is a general model already studied for these iron-based superconductors. It includes all the 5 orbital models. And then it contains a titanium part and also the interaction part, basically including the local Coulomb interactions and the home-through coupling. And to solve this very complicated model, we propose a so-called U1 slave spin method. And for details, I'll just refer to these two references. So basically, a simple idea of this method is to introduce a spin 1/2 slave spin and a fermionic spin-on operator to carry the charge degree of freedom and the spin degree of freedom respectively. And then we can further apply a constraint to limit these slave operators in their physical Hilbert space. Then we re-expect these slave spin operators in terms of a Schringer-Boson representation by introducing a draft operator, this Z, which stands for this quasi-particle spectral wave. And then we decompose these slave spin and spin-down operators to get the saddle point equations. And by solving these two coupled saddle point equations self-consistently, we obtain 3 possible solutions. So one solution is just a normal metal, where the quasi-particle spectral wave Z is non-zero for each orbital. And the second solution we got is a multi-insulating phase, where the Z value are all 0 for all the orbitals. And interestingly, the system can stabilize a third solution, which is exactly the orbital selective mode phase, where the Z value are 0 for several orbitals, but non-zero for other orbitals. Okay, so then we apply this slave spin method to study or to understand the orbital selective mode behavior in the iron telluride system doped with selenium. And recently, an RPAS experiment revealed that by reducing the selenium concentration in this system to the iron telluride site, the system can undergo a transition to an orbital static mode phase at low temperature. And this caused a reconstruction of the Fermi surface where the spectral waves with the dz square orbital character appear around the X point of the brane zone. And this is just discussed in the Dr. Zhang Huang's talk yesterday. And this transition to the orbital selective mode phase and also this reconstruction of the Fermi surface has already been well described by our slave spin method. Okay, so then I'll turn to the to discuss the correlation effects and the orbital selectivity in this bilayer nickelate superconductor. And our work has recently published in PIB. So first of all, we need to construct a effective model. And we noticed that by a simple valence counting, that in this bilayer compound, each nickel ion carry a valence of 2.5, which actually means that there are 7.5 electrons occupying these 3D orbitals. And then because there is a very large level splitting between the T2G and EG sectors, so 6 electrons are occupying this T2G sector, and only 1.5 electrons occupy this 2 EG orbital, which have either this Z square or this X square minus Y square orbital. And then considering this upper and lower layer of the nickel ion. So each unit cell containing these 2 nickel ions. So we have 3 electrons occupying these 4 orbitals. And we also see that the hopping matrix in these 2 EG orbitals should be very anisotropic. And in particular, there is a very strong hopping between the upper and the lower DZ square orbitals. So they have a very strong bonding tendency. So then we propose this minimum model, including the 2 EG orbitals and in the bilayer system. So then to describe this strong bonding effect between the upper and lower layer, the square orbitals, we perform a rotation in the orbital basis so that we describe the system in the bonding and anti-bonding molecular orbital basis for this DZ square orbitals. So there's this bonding state and anti-bonding state. And then we also perform this transformation to this interaction Hamiltonian in this molecular orbital basis. And then we adopt 2 theoretical approaches. And in the first approach, we can simply further simplify the system by assuming that since the DZ square anti-bonding state has a very high energy level, so we can further simplify it by assuming that this state is almost empty. So this can be done in the calculation by assuming that the electron filling number in this anti-bonding state is fixed to its U equal to 0 case. And then in the second approach, we're gonna release this constraint by performing a full calculation. Okay, so now I will give some results first in this first simplified approach. And here is the ground state phase diagram in the J Holmes versus U plane. And we find that when increasing the U for fixed Holmes coupling, and we see the system undergoes a very broad crossover from a low spin state to a high spin state. And further increasing the U value, we find the system undergoes a transition to a orbital selective mode phase. And just near the boundary of this orbital selective mode phase, the quantum-particle spectral waves are substantially suppressed, very close to 0. So it means that the system has a strong orbital selective electron correlation effect. Okay, so then this strong correlation effects suppresses substantially the overall bandwidth of the system, which is seen in this dense cell states for the d orbitals. And also it causes a strong orbital dependent band renormalization. And in particular, there is a very flat band just lying in on the Fermi level, which has the Z square orbital caricature. It also causes a renormalization to the Fermi surface. And first, we look at the non-interacting case where U equal to 0. And the Fermi surface contains 3 sheets. The alpha sheets mainly have the x square minus y square of the character. That is a circular electron pocket near the zone center. And the beta sheet is a large hole pocket, which mainly have this x square minus y square of the character. This is very similar to that in the doped couplet system. And also there is a third sheet, the gamma sheet, which mainly has this dz square of the character in the calculation. And this one actually resembles that of a heavily hole doped iron nuclide. Okay, and once we consider the electron correlations by taking this U to 5.3 electron volt, and we see that the sizes of this of all the Fermi pockets are somewhat renormalized, but their shape remain. All right, so to understand the strong optical selectivity in this system, we propose this global phase diagram by including the a by artificially increase this electron filling from 3 to 4. And we see that the real material actually corresponds to the electron filling of 3 electrons. So it is still a commensurate filling. So we expect to see a transition to a multi-insulating phase at sufficiently strong U value. But at reasonably large U value, related to the physical regime of the system, we only see a transition to a orbital selective mode phase. And if we increase the electron filling to n equal to 4, the system is exactly at half filling, and we can see a transition to a multi-insulating phase at a much lower U value. And the orbital selective mode phase naturally appear by doping this multi-insulating phase at half filling. So then this scenario are fully supported by our calculation in the slip spin method without the constraint, that is the full calculation. So then at n equal to 4, as shown here, the quantum particle spectral weight goes to 0 in all the orbitals when increasing the U to a critical value. And we see that all the orbitals are at half filling here. And by decreasing this total electron filling to n equal to 3, we still observe this transition to a orbital selective mode phase. And also there is a low spin to high spin crossover, a very broad crossover in the doped system. If we regarding that the n equal to 4 as the parent phase. Okay. And then the high spin states actually correspond to the dz square orbitals are in half filling, and the x square minus y square orbitals are at quarter filling. And very interesting, we also observe that the correlation stress of this dz square bonding state, which is identified as this black curve shown here, and it behaves a very strong. It becomes very sensitive to the total electron filling. So by just increase the electron filling a little bit, and we see that much stronger electron correlation effect with much smaller z values in this orbital category. Right. So then with this theoretical result, we are trying to understand some aspects of the experiment. So first is about the RPAS measurements. So in this experiment by the Xinjiang Zhou's group, they actually measured the effective mass enhancement along different costs in the brain zone, and find that there are very strong orbital dependent effective mass enhancement. And for bands related with this x square minus y square orbital, and they see that this mass enhancement factor is about 2 to 3. Well, for the bands with this dz square orbitals, this factor can be as large as about 5 to 7. So we did the calculation on this band structure, and following the exactly the cost in the experiment, and also calculate these mass enhancement factors at several different U values and for several different electron filling numbers. And we find that by either increasing the U value or increasing the electron filling number, we can both see this mass enhancement factor becomes strongly orbital dependent. In particular, for the bands with this x squared minus y squared orbital capture, we see that this factor is between 2 to 3, which is consistent with RPS value. However, if we focus on the CON4, CON5, which are the bands related with these square orbitals, then if we fix n equal to 3, we find that although by increasing U value, there is an enhancement of this factor, but the value is still much smaller than the measured value in the RPAS. However, remember that this band has a orbital character with a z-square bonding state, which is called this gamma band in the experiment. And then remember that we just discussed that this orbital has a very sensitive orbital selective electron effect, which is very sensitive to the total electron filling number. So by just increasing a little bit of this filling number, we see that this mass enhancement, particular to this orbital, enhanced largely. So this could be one explanation for this experimental observed value. But definitely there could be alternative explanations, because in the experiment, actually, this band is slightly below the Fermi level. However, in our calculation, it is still crosses the Fermi level. And then I will briefly discuss the connection to the optical conductivity measurements. And here I show our calculated optical conductivity with this XY in plane with this in plane polarization. And we see that with the electron correlation, this spectral weight in all the frequency has been suppressed. And around 1 electron volt, we observe several peaks, which are consistent with the measured one. And in particular, at low frequencies, we see a suppressed druid weight, and correspond to the kinetic energy of the electrons is reduced by a factor of about 60%. But this value is still much larger than the observed value. But definitely there could be several mechanisms for explaining for this further reduced measured kinetic energy in this optical conductivity data. For example, this very sensitive orbital selective correlation effects with doping concentration. Okay, so next I will move on to the superconducting pairing in this bilayer nucleate.
Actually, I'm sorry to interrupt, but we're kind of at the end of time. So if you could wrap up.
Okay,
cool.
Thank you.
Thank you.
Okay. Yeah. So so I just said that we consider the parent compound, parent phase is actually a putative half-filled melt insulator. And we can understand the real system by doping this most insulating phase, so that we can derive a multi-orbital TJ model, including both the x squared minus y squared and this z squared orbitals. And then there include is hopping term, which is renormalized by this electron correlation effect, and also there's an antiferromagnetic super exchange term. And by decomposing this super exchange into the different pairing channels, we can self-consistently solve this model for the superconductivity. And here the relevant model parameters are the in-plane exchange couplings in the x squared minus y squared and these z squared orbitals. That's the JXX and the JZZ. And by increasing this ratio, and we see the system can behave either a A1G with an extended X wave pairing or a B1G channel with a D wave-like pairing. And the Fermi pockets with different orbital characters can promote either the S wave or the D wave pairing in a way compromise to this super exchange coupling. All right. So I'll just stop here, and here is a summary of my talk, and thank you very much for your attention. Sorry for the delay.
Thank you very much. Sorry, I was just worried there was a second half, so maybe I shouldn't have interrupted. My apologies. So this is open for questions or comments. Maybe I could start out with one. So, of course, the materials, I'm sure we'll hear more tomorrow, but there's all these related issues of stacking faults, or maybe tri-layer is okay, bi-layer is okay, etc. Does that robustness qualitatively surprise you, or it's kind of, reasonable with respect to kind of the theoretical scenarios you're looking at?
Oh, that's interesting. So I mean that there could be either this bilayer or tri-layer, or maybe is this infinite layer. So theoretically, I think one way to understand is this is probably I'll just go back to this global phase diagram. Here. Okay, so basically, one way to understand this theoretically is, I think, according to this global phase diagram. So we see that the infinite layer would correspond to almost a D9 state, which is actually not shown here. It's actually a system which has a different D electrons, and then go to this bilayer system. So we see that there is this D7.5. So the electron filling are definitely different. And then we actually are interested here in this regime of the global phase diagram. And definitely, according to the different electron fillings, we can work with in the different parts of such phase diagram. So in different parts of the phase diagram, definitely the electron correlation effects could be very different. And also there can be also this material dependent behaviors. And we need to consider it more carefully. Yeah.
Christine, please go ahead.
Hi, thank you for the very interesting talk. I just want, maybe you can elaborate a little bit more about the analogy between the iron telluride when they have this mod transition because of the complete localization of the DXY band versus 327 nicolites, and what drives the system into this mod transition.
Okay, so you mean probably this one, the iron telluride system?
Yep. Exactly.
Yeah. So here I think this is called the isovalent. It's a so-called isovalent doping. So it means that if we dope this selenium in the system, basically these two elements has or the two ions has exactly the same balance, so that there's no electron dope to the system. So basically, this actually changes the bandwidth of the system, or changes the Hawking matrix, the Hawking integral in the system between this bandwidth. So in this nickel-plate superconductor, so I think this is a very similar. It's a very similar way. So basically, it's tune this U over T. And then there we also see a optical selective mode phase if we increase this U over T ratio. So I think this is in a way similar to this iron-based superconductor.
Okay, so does it mean that it's the pressure tuned by pressure that it will drive the system into the mod insulating state, the more selective state?
In this nickel system, based on our calculation, we indeed find a transition to a orbital selective mode phase, but it's very hard to get into a real mode transition into this mode insulating phase. This is partly because this filling number is a little bit different. So it's 3 electrons occupying these 4 orbitals, something like if we understand this according to this global phase diagram, this state, this most insulating state would have a very large threshold value of U. So it's not easy to be stabilized. But in the iron-based superconductors, we already see it in the model calculation. It's kind of much easier to stabilize such a multi-insulating phase. That's because of the different electron filling number. Yeah.
Thank you so much.
So,
Thank you. Are there any
Right.
final
Thank
questions?
you.
Okay, if not, thanks, Professor Yu.